So we are going to continue working on the, I mean, again, just to, I think this is very nice that we are using the same data set across different sessions. And so we are going to be using the same sea surface temperature data set. And so again, just for, as the previous presenters have done in their own hands-on session, I will not be running these code blocks, but I really strongly encourage you to run them on your own collab session. And the only reason I'm not doing that is because we already have the output, so I'm just going to be using them to make sure that we can walk through all the different parts. Right. So as we discussed, so we are going to be using DeepHyper to, in some sense, minimize both the validation error that we were previously doing on the sea surface temperature data set, but we're also now going to be looking at the number of parameters. So why number of parameters? So as I mentioned it here, so this is actually a good proxy for many things. It's a good proxy for the model size. So you can think of it as its memory footprint, roughly. Also model sparsity, also model efficiency, because the fewer parameters you have in your neural net, you're generally going to be doing fewer number of operations on it. So like the fewer number of multiply add operations, for example, as well as, in general, some measure of prediction time. So, all right. So just to, again, recap, this is again, just, I guess this is something that you have seen before if you have been following us, but in case you have not, this cell just, make sure that you're kind of making sure that you're in Colab and, installing getting the right packages. It'll just make sure that we get the data set that we have posted on this Git repo that will.
I'm sorry to interrupt. Could you zoom in a bit? It's a bit small for my eyes.
Oh, okay, sure. Yeah, thanks for pointing that out. How is it? Just tell me when to stop. Is it good now?
Yes.
All right, thanks. Yep. So, make sure that you, if you're just joining us, in case you were not there for the previous session, but after you run the first cell, make sure that you restart the runtime so that we actually load the correct packages. So yeah, so as it says here, you can also change your runtime to select the TPU, which will make sure that everything runs a bit faster. Yeah, I think so. The way you do that is you go to runtime and you just say change runtime type, and there you can select your TPU. So this is exactly as before. Again, I encourage you to again run this. So this is we are going to load the data set. This has already been kind of done for you. So you just have to make sure that you load your training and testing data set from here. So I mean, just to Romit went over this very well in his talk, but essentially this data set is a three-dimensional data set. For every latitude and longitude on the Earth, it kind of gives you the weekly average temperature for that particular latitude longitude pair. And so we are using a baseline Lstm model, which I'm not going to go over simply because this has been covered multiple times in the presentation. But essentially, it is a baseline model which comes up with a default set of configurations for in terms of hyperparameters. So you have a number of different Lstm units, the different types of activation functions, the learning rate, batch size, and so on. And so if you were in the session that Romain presented, this is exactly the same as that. There is literally no difference. And so what you can do is you can actually run, get the baseline model, and you can just I guess I should not have done that, but okay. Oh, that's because I cannot run this. But I think you can run. It is okay to run that. So it does run, and it will. What you can do is I'm just going to quickly skip ahead while it's running. But the two things I kind of want to point out is you can actually look at the validation loss of the baseline model And this is the one that we're going to be using as a baseline. So 0.01, 1e minus 2, and you can also check the size of the baseline model, right? And so, so we here, for example, we see if you just print model summary that this model has roughly 70,000 or so trainable parameters. All right. So this is the baseline model. And so now what we are going to do is we are going to see how we can optimize for both these two things, right? So both the validation loss and the number of parameters. And so this, so the first thing you have to do is you have to first set up your search space. So in some sense, you're going to define the domain over which you're going to search your hyperparameters. And again, this is exactly the same as what Roma had. The only thing is, I think I removed the number of epochs as a hyperparameter just to make sure that this notebook runs a bit faster. That is really the only difference, but there was no other reason to remove it. And so you can actually see that we are searching over a number of LSTM units that varies between 10 and 256, and this is, and along with the number of layers in your neural net, this is going to essentially dictate the size of your model, and everything else in some sense is going to be in charge of making sure that you get a small validation loss. And so I have this here, but I'm not going to run it. But this essentially shows that this is the run function that you have to define the objective function, right? So now in the single objective case, we simply had this, right? So this is the single objective run function exactly as before, where we are trying to minimize the validation loss. So DeepHyper actually is configured as a maximization problem. So if you return the negative of this, you'll actually end up maximizing the negative, which means you'll end up minimizing the validation loss. And so you can actually run the centralized Bayesian optimization algorithm with this particular run function here in this cell here, where you just simply pass the run function as an argument along with your search space definition, which is this problem object here. And you also specify, for example, the directory where you're going to log the results, and with a maximum of 20 evaluations. And now, so after we run it, you can essentially query this results object to get the best configuration. And so this best configuration, again, the one thing that I want to look at is you want to check the validation loss, right? And so remember that our baseline model had roughly 0.01, but after we actually run this, the two things again we want to look at is the validation loss, which is now, as we can see, it has actually decreased from 0.01 to roughly 0.003. So that's one thing, but you can also actually look at the model size, right? Now, it's important to note, the reason I want you to check this is because when you do a classical single objective, hyperparameter search, this is not something that we are optimized for, right? So we find that we have about roughly 125,000 parameters. So notice that so if I go back and if I look at the number of parameters in the baseline model, that was roughly 70,000. By essentially adding, a lot more parameters, so 120,000, we can actually reduce the validation loss, right? And now you might say, okay, that maybe this is a bit too much for you, for your particular application. Maybe you want to actually try to reduce this number. And so the way we do that is actually very easy, right? So there's actually no difference. So the only difference is we change the run function. I just, call it something else. You don't have to call it something else, but I call it, run to objective. And so along with the validation loss, we now instead return a tuple of objective functions that you want to minimize, right? So along with this, we are now also trying to minimize the number of parameters in your model, right? So we do that with this simple function. We simply count the number of parameters, and so this run function now is returning both the validation loss and the number of parameters. And what you can do is everything is exactly as before, nothing changes. So you just pass this new run function, which is returning this tuple to the centralized Bayesian optimization function, which is CBO, and DeepHyper will automatically detect that you actually have two objectives, that you're returning two objectives, and it will simultaneously try to, in this case, optimize for both of these objectives. And it does that using a default, multi-objective strategy. But this strategy can be changed by passing additional arguments, which I'll come to in just a minute. But everything else is exactly the same. I've only changed the logging directory here. That's literally the only thing that's changed, just to make sure that we push the results in a different, in a different folder, and we can retrieve it later if we want. And so then after you do that, what you can do is you want to now actually visualize the different configurations that DeepHyper has, has in this results data frame. So the one thing, maybe the only thing I'll maybe show here is that the progress bar actually changes. So instead of reporting the objective, it actually reports the sum of the objective functions, right? Now, this is only for logging purposes. This has no effect on the search, but this is again, and this is actually important to note also because the objective functions have very different scales, right? So because your validation loss is something like 0.001 something, whereas the number of parameters is like roughly, 6 orders of magnitude higher. It's like in the order of 100,000, right? So it's important to note that DeepHyper actually internally rescales these, and then it's trying to optimize them. So again, this is only for logging purposes. Anyway, so after you are actually done with the optimization, you can visualize the different, configurations that DeepHyper was able to obtain. And so the way you do that is you just look at the data frame, and you just look at so there'll essentially be a column called objective 0 and objective 1, and if you have n objectives, it will be objective 0, 1, 2, 3, so on. And so all I'm doing here is just plotting these different objectives. So on the first axis, we have the first objective, which was our validation loss. I've just negated it because that's what it physically means. And then on the other axis, I've shown the number of model parameters. And again, the only difference is I'm putting it on a log scale just to get everything, all the configurations in one plot. So the important thing that I wanted to kind of see here is that DeepHyper is actually able to explore many different configurations. And amongst these, the ones on the red, which you can actually get using a convenient function that we provide within DeepHyper, is you can actually get the best configurations using this function called the Pareto front. You just pass the objective values, and it will automatically compute the best of all these configurations for you, which do not dominate any other objective. And so you can actually show them explicitly in the plot, and we see that. So this is just a standard scatter plot. There's nothing special going on here. And you actually see that it's able to identify these 5 configurations which improve upon the baseline, both in terms of the number of model parameters as well as in terms of the validation loss, right? So observe how you have models which are very small. So if you have fewer parameters, you typically tend to have very large values for the validation loss. Although that's not true, there is this one configuration here, which actually, sorry, I'm sorry. Yeah, that's true. So you do have models which hyperparameter configurations which result in a small model size, but they have a typically large validation loss. But then, as you try to put more and more parameters, you effectively get a smaller validation loss, but then you end up growing your model size. Right? So this is exactly the kind of trade-off that you want to look at. These are the kinds of configurations you want to look at before you decide which one to go for, right? So, and you can actually see which ones these configurations are. So if I just look at the object that computed this, so the Pareto front, if I look at these red configurations, the validation loss varies from 0.01 with a corresponding number of parameters, which is roughly only 1,000, right? To all the way, roughly to something that we got, which was very close to a single objective case, so 0.004, but with many more parameters. And again, so the baseline had roughly 70,000 parameters, so we are able to significantly reduce that number of parameters by using our Bayesian optimizer. You can also actually look at the actual configurations, right? I mean, this is ultimately what you want. So you can actually look at the Pareto optimal hyperparameter configurations, which produce which resulted in these red points on this objective space. And so you can again do that with this convenient function called non-dominated set, right? So you can just get this non-dominated set, and you can look at those configurations. And so again, here we see you have configurations with few layers, few LSTM units, as few as 13, with this particular error, validation error. But you also have some larger ones with that particular 0.004, for example, in this case. So yeah. So the key takeaway that I want you to notice is that nothing really has changed. I mean, everything is exactly the same. The only difference is you just pass, you can make sure that in your run function, so you have just one run function, and within that run function, you compute all your objective functions, and you make sure that you pass all of them, you return all of them in your run function that you want to optimize, and then DeepHyper will take care of the rest. Now, I just want to pause here for some questions. I mean, I do have some extra stuff, but if time permits, I'll go through it. But if there is no time, I'm also happy to just leave it, and I can let you. The notebook is completely self-sufficient, and you can actually, go through it yourself. But how are we doing on time, Prasanna? Should I continue, or should I?
We can pause for a couple of questions,
right.
and leave this as an exercise.
Absolutely.
For the participants. So we are almost at the end of the day. So
absolutely. No worries.
Cool. Thank you, Anirudh. This is fantastic. Okay, so questions. Yeah, so there is the notebook. Please do play with the notebook, and we will be putting some documentation on this very soon. As we speak, we are sort of merging this into the main branch and so on and so forth. So I think this is still in the develop branch, but as soon as we have this is in the release.
No, this is in the release. Yeah.
Sorry. Yeah.
So just make sure that if I go up, just make sure that you're using 0.4.2.
4.2. Okay.
Yeah. Exactly. Yeah.
Excellent. Yeah. This is fantastic. There are many ways that one could potentially think of using multi-objective optimization. For example, you can parameterize the sparsity, and you have probably seen hundreds of papers written on sparsifying models and so on and so forth. So this is another way to think about how to sparsify the models, or expose the sparsity parameters and then optimize and do several things on top of it. So please do. Yeah, go ahead.
No. Yeah, exactly. And I mean, I encourage you guys to play with this and just come up with different objectives, and we're happy to hear your feedback and keep improving this. Exactly. Yeah. Just to reiterate what Prasanna said.
I have a quick question. By the way, it was a great talk. So, is there any suggestions or preference on the scalarization strategy? Is that for a particular problem? Is there any way to? Does it depend on the number of objectives or problem characteristics?
Right.
Is there something?
Yeah, so we are actually documenting all of that, and we should have a paper out soon. But right now, the second part of the notebook, which I did not cover, actually does talk about some of exactly those questions that you raised. So, for example, because right now the way I expose the CBO interface, it does not really it just uses a default strategy for everything without actually telling you what the scalarization is. But so, for example, right, so this is actually, I mean, if, maybe just go through the rest of the notebook in 2 minutes just to answer your question. But this is essentially, one of the high level takeaways was that takeaways from the second part of the notebook is that, for example, if you have a problem, which is like, this is a test, this is a small test function, by the way, multi-object optimization. But if you have a search space that is purely continuous, right? So one thing that you can do is you can, first of all, make sure that, you use this strategy, which actually, so the default strategy, for example, in this test function, explores only a small part of the search space, because the way it's configured is that it DeepHyper just gives equal preference to all your objectives by default, right? So if you notice here, so roughly in the 0.5, 0.5, direction, which is this, or the 1, direction, I should say, that's where most of the Pareto points have been found, right? Now, what you can do is actually, you can come up with a scalarization, which is, which you just prefix it with this letter R. And what this R does is that it will use the Chebyshev scalarization, which is the weighted infinity norm, and it will just come up with, different weight preferences, and it will try to optimize all of them in different iterations. That's all it's doing, right? So instead of just looking at the 1, direction, it will just try to sample different weight directions, preference directions, sample different preferences, so to speak, and try to optimize them, right? And so if you run the same function with that kind of, configuration, you'll notice that you actually get a much wider distribution of points on the Pareto. So that is something that you can certainly try out. I should mention, right? So this is all, again, in the centralized framework. When you go to the distributed framework, that's when we feel like the real power of this is going to show, because you're actually using different parts of your different different workers to essentially explore different parts of the Pareto plan. But this is still that is still under active development, and that is not in the release branch yet. So.
Okay. Oh, one more question. So, if there is any constraints on the objective value, will that be able to be used? As in, if there is a max value of an object.
So do you mean to say you want to restrict your search space further by saying that, okay, minimize objective 1 and 2, but also look only at those points on your search space where objective 2 is between 0 and 1, yes, for example?
Yes.
So that is something that we don't have, but it is something that we can accommodate within the multi-objective framework by essentially using a penalty approach. Because you can essentially convert that, constraint on the objective to another objective, essentially, so to speak. But we are not, we don't have that. But if that is something that is of interest, we can certainly talk offline, and we can think about, getting that implemented. It's certainly not hard to do. It's just that it's not currently part of the.
Yeah, thanks, Anirudh. Yeah, I actually have something like that. I'll reach out to you.
Absolutely. Yeah, I'd love to hear more about that.